Power factor correction. We're going to take a look at why we do power factor correction in this presentation. Let's take a look at a typical factory that all of us have seen on the side of the road. It's usually gray with 3 smokestacks belching all sorts of goodness knows what kind of pollution out into the atmosphere. And it has a poor power factor. All of us inherently know that large industries that utilize motors or some form of inductive heating will have a significant amount of VARs that are required by the supply authority. So the supply authority, or BC Hydro, is going to have to provide not only the in-phase watts, but also the out-of-phase VARs. And so what we can consider this as is 2 separate channels of current. There's in-phase current and there's out-of-phase current. And both of them together combined make the total power or the total current that would have to flow on the conductors to supply this factory, which is making, I don't know, rubber chickens. And as you can see down here, it's got a relatively high current because BC Hydro has to provide both. Now, this is fairly important to understand that BC Hydro has to provide both of those power values to the factory. In power factor correction, what we do is we take advantage of what we understand about VARs and out-of-phase power, and instead of requiring BC Hydro to provide it, we simply provide it with a capacitor bank that's located on the premises. In doing this, what we have accomplished is a decrease in the amount of current that comes from BC Hydro, but remember, is the total amount of watts any different? Total amount of watts that we are requiring from BC Hydro hasn't changed, but the total VARs that we required has changed, and that has made an effect on the total current. So remember, capacitors and inductors store and release energy at exactly the opposite time, which means that the capacitor bank is playing a game of catch and release with the inductive loads inside the factory. So how have we saved any money then? Because you're probably sitting there going, well, Dave, I mean, honestly, if the power has not changed at all, like we're still using the same amount of watts, and you're thinking in the back of your mind, well, obviously kilowatt hours is how an industrial consumer is billed, as well as a residential or a commercial consumer. Then if the power hasn't changed in watts, then how can their consumption value change or any sort of cost effectiveness be had here? And if that was the end of the story, I would agree with you and we would be done the discussion. However, BC Hydro understands that if they have to provide more current, that is a tax on their infrastructure. And so what they do to recoup these costs is they try to put in a levy or a tariff on the amount of out-of-phase current that they have to provide. So here's another example just showing where this current would be coming from. Up here, this is all of the current coming from BC Hydro to the motor. Whereas now, if we supplement the current with a capacitor, now the capacitor provides that out-of-phase current, and BC Hydro only has to provide this value here, depending on what the power factor is of the motor. So how do they recoup that chart or that strain on their infrastructure? Well, they apply a surcharge. And so this is a table that has just been taken from BC Hydro's website, and we can see that for a large industrial consumer, there's actually quite a few things that go into the overall cost of their energy use. Remember, they charge kilowatt hours. Kilowatt hours. And so with new electronic meters, what they're able to keep track of is kilovar hours as well. And what they do with this information is they can then calculate what power factor your facility is operating at. Take a look at what the surcharge is. This surcharge is saying we will take 4% of your consumption and we will add that to your total bill. So let's say you have a total demand charge, like the amount of consumption you have, of $200. Well, what they're going to do is they're going to take that $200 and they're going to apply 4% to it. That's $8. And they're going to charge you $208. What if you have a really poor power factor, though? Let's say you're down here. You have a power factor that's in, and you'll notice power factor is sometimes given as a percent or a decimal. But let's say you're operating at 60% power factor and 57% is your surcharge. Well, let's go to the same example. You have $200 that you've paid for your consumption of power. 200 times 57% is $114. Add that to your 200. Guess what? If you're this consumer down here, you've just paid $314. And so they make it more and more and more because they want people to move up the chart so that they have no surcharge. And what that means to BC Hydro is they have to provide almost no out-of-phase power or out-of-phase current. Remember, if the current flows on the wires have to be big enough to handle it. The transformers have to be big enough. Everything has to be big enough. And so by applying capacitors, we can lower the amount of current that is then provided by BC Hydro to us, the consumer. Now, this type of surcharge does not happen in a residential or small commercial application. It's only the large consumers that have this applied to them. So what do? We add capacitors. Here's a capacitor. There's a whole bunch of capacitors. And with power factor correction, we need to be able to adjust how many capacitors are online at any given time, because we know that the electrical load inside the facility will vary. It's never going to be a static 100 amps. Lights are going to turn on and off, motors are going to turn on and off, and because of that, the reactive component of current will get higher and lower. And so for active power factor correction, you need to have multiple arrangements of contactors with groupings of capacitors, and those contactors engaging and disengaging depending on what the power factor is on the line. You can have smaller installations like this or very large installations. And at a certain point, it becomes advantageous for us to get a form of power factor correction, with something with leading VARs that is more adjustable than simply connecting capacitors in series and in parallel. This is a shot of three-phase capacitors and some of the ratings. So the type of device that we would typically use if we wanted really precise adjustable leading VARs is something called a synchronous condenser. And a synchronous condenser, you can think of it as a motor that has no shaft coming out the end. All we do is we run it, and you'll learn about it in future years of training. In running this object, we get leading VARs. And those leading VARs we can then use to cancel the lagging VARs of the system. So power factor correction is a immensely lucrative area of the electrical field, which large engineering firms will apply in the design specs when we start looking at manufacturing predominantly, because manufacturing has so many motor loads associated with it. This is some of the main switchgear at another post-secondary education facility. And what we can see is that on the displays for each one of the buildings, the energy on site for the consumer is actually read here. The real power in megawatt hours, 78,000 megawatt hours. The reactive VARs, 48,000. And the apparent, the overall SVA, 92,000 VA. So in this facility, a significant reactive VARs is still being provided by the supply authority. So I hope this gave you a good background as to why we would want to power factor correct. Take a look at a future presentation where we look at calculating